Hello student, my name is Shayan Mitra. I am the faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management, JISP. Today I am going to take the class of Embedded System Design. The subject code is EC703B. This is the lecture number 8. In the previous lecture we have been discussing about the mutual exclusion, deadlock. After that we discussed the last synchronizations, how we get out of all those deadlock situation using semaphores, and we have described the different kind of RTOS system. So from this in this slide we have discussing the characteristics of real-time operating system. In case of real-time operating system, the RTOS for embedded systems are single purpose, small size, inexpensively mass produced, specific timing requirements, such as washing machine. It has a very not that big size, and it's a very single purpose, small size depending upon the thing that we are using here. Inexpensively mass produced, and specific timing requirements are there for RTOS. And features missing in RTOS are support for variety of peripheral device, protection and security mechanism, multiple users, multiple modes, and dynamic allocation of memory. All these features are missing in RTOS. So let's go to the next slide. So why the disadvantages are present in real-time operating system? Real-time systems are typically single purpose. Real-time systems often do not require interfacing with the user. Features found in a desktop PC require more substantial hardware than what is typically available in a real-time system. High overhead required for protected memory and for switching modes. Memory paging increases context switch time, creates fragmentation, adding to timing unpredictability. All these points really want to mean few very important points here. That support for variety of peripheral devices. This feature has been missing. Why? Because this real-time operating system has been used in embedded system, and embedded system is very much it has very limited functionality. Okay. Suppose we are using a microwave, or you are using a washing machine, or using a digital camera. So all these are single purpose, and these are being hardware or designed, and the software that has been embedded within the hardware system are very much has the very much have the aim of providing a very specific functionality which does not need to include different other peripheral devices, such as in case of a washing machine, in case of a digital camera, we really don't need that much amount of peripheral devices. So for that very reason, the real-time operating system does not support that variety of peripheral devices. You can use two, three peripheral devices. Those are very much related to this much related to the device which has a very few or specific functionalities. Related to that, we can use the peripheral devices. But other than that, if we have to compare with a PC, there is no match. In case of a PC or in case of PC, we can use different kind of peripheral device. We can use a printer. We can use a different kind of interfacing devices that can be used in case of PC, because that piece in case of PC, the general purpose processor, the hardware is much more complex. We can read and write different kind of software. The PC can be act according to the software that has been used to burn into the hardware, and so on and so forth. But in case of embedded system, we don't have that kind of flexibility, because the hardware that has been embedded within that system is much more less complex. The architecture of those OS are much more less complex. So number of software that we need to inducted in a real-time operating system or an embedded system is far-fetched imagination, I would say. So support of peripheral device is not important. But the case of protection and security mechanisms that we have already discussed in previous lectures, that as because it has very limited functionalities, the security mechanism of this kind of devices are not that very much upbeat. Okay, so the multiple, as you can see that we can't use multiple users in case of embedded system. So these are the facts. So that it has been described here. The real-time system are typically single purpose. Real-time systems often do not require interfacing with the user. Features found in a desktop PC require more substantial hardware than what is typically available in real-time system, that we have already discussed. And high overhead required for protected memory and for switching modes, because we need to have switching modes. The high overhead required for this protected memory. Memory paging increases the context switch time and creates fragmentation, adding to timing unpredictability. So let's go to the next one. So next one is the scheduling in a RTS. So in case of scheduling, in case of a retail operating system, what we basically use the handling priority, scheduling algorithms, meeting deadlines, avoiding conflicts like deadlocks, and real-time system development. So in case of scheduling RTS, handling priority, scheduling algorithm, meeting deadlines, avoiding conflicts like deadlocks, real-time system development are also being used. Next one is event latency. Now, if you have to understand what is latency means, latency is basically the in one word we can use the word. It is basically nothing but a processor speed. Okay. So if you have to describe what is latency is, it's basically the processor speed. Suppose as a digital camera, we have selected a picture. We want to catch that picture practically. So we want to suppose I have clicked the picture, and that picture taken a time to process and come to the output screen is 0.25 seconds. So that 0.25 second is the latency of that very specific device. Okay, so it is basically define the latency or the processor speed of a device. The event latency is nothing but the amount of time from when an event occurs to when it is serviced. In real-time system, this latency should always be within a particular limit. This is known as responding to real time. Scheduler part of the OS to be configured to respond in this manner. It means this kind of as because it is all the embedded system are being designed to cater some kind of very specific functionalities. So all those functionality are need to be very time driven. So that's why the event latency is very much considering in case of embedded system design. Now the real-time CPU scheduling. It is its periodic process requires the CPU at very specified intervals. P is the duration of the period. D is the deadline by when the process must be serviced. T is the processing time. By ensuring CPU responds within the given time interval, real-time response can be guaranteed. Now suppose the periodic process requires the CPU at specified interval. P is the duration of the period. So P is the duration of the total period. D is the deadline by when the process must be serviced, and T is the processing time. So this is the processing time, this is the deadline time within which the process must be serviced, and P is the duration of the total period. This is the real-time CPU schedule. By ensuring CPU response within the given time interval, the real-time response can be guaranteed. So by creating a deadline within a deadline is basically helpful to reach the time stringent conditioning. Through which that if suppose it failed to complete the submission here, it will be easily completed the time stringent criteria within that specified period time period. So let's go to the next slide. So this is the real-time CPU scheduling, and the periodic process requires the CPU specified time. P is the this we have already discussed. The next one that we want to discuss is by ensuring CPU response within a given time interval, real-time response can be guaranteed. Priority-based scheduling and earliest deadline first scheduling. So this is the priority-based scheduling. Then according to the priority, that according to the scheduling will occur, and the earliest deadline first scheduling. So the RTO's issues are interrupt latency should be very small. That I have already discussed. The kernel has to respond to real-time events. Interrupt should be disabled for minimum possible time. For embedded application, kernel size should be small, should be fit in a ROM. Sophisticated features can be removed. No virtual memory and no protection. That is the issues of the RTOS. The RTOS characteristics are reliability, predictability, performance, compactness, scalability, user control over OS policies, responsiveness, fast task switch, and fast interrupt response. So these are the RTOS characteristics. And examples of RTOS are Linux OS, OSC, QNX, VxWorks, Windows C, and RT Linux. So up to that, what we have understand that how the RTOS works, what is the issues of RTOS. So up to that we have described all this. Now from this slide we are going to describe what is the multiprocessing means, what is the multi-threading means, and what is the multitasking means. What we have discussed earlier, that we have understood, we have a very specific knowledge about task, very specific knowledge about process and task and schedule. So we are going to get a very simple idea of thread. What is the kernel? The word kernel means. So all this, the deep analysis of all those things will be will start in this lecture also, and we will be continuing this lecture up to the, and we will continuing this discussion into the next lecture also. So let's begin with this slide. That in this upcoming slides we are going to discuss, we will going to explain the difference between the multitasking and multiprocessing, explain the difference between the multi-threading and multiprocessing, list several disadvantages of achieving multiprocessing by using multiple MPU packages, explain the difference between cooperative and preemptive multitasking, explain the difference between symmetrical and asymmetrical multiprocessing, and discuss the internal structure of the Pentium D, Core 2 and Core 2 Quad processor. It's basically a overall overview. We are not going to get into the very deep analysis of Pentium D or Core 2. So those are not necessary. So we are just going to give you the overview of the internal structure of all those Pentium D and Core 2. So the basic feature that we are going to cover in this section here, that we are going to understand the multiprocessing, multi-threading and multiprocessing, multitasking. There are two kinds of multitasking that we have discussed earlier, the non-preemptive and preemptive. So we are going to understand all those things with examples. So okay, so let's go to the next slide here. Now the first thing that we understand, the multi is more than what, and what's the multi means. So we have listed four things. One is multitasking, one is multi-threading or multi-threaded, another one is multiprocessing, another one is multi-core. So let's go to the next slide. That now we are going to understand all those four things differently, and we are going to understand that what are the basic differences and how all these four parameters or terms are interrelated. So let's go to the next slide. So first one is multitasking. What is multitasking means? It's very much similar to tasking. The slide is saying that the apparent simultaneous execution of two or more programs by a single processor. So if you're talking about multitasking, so this is the basic definition of multitasking, that the apparent or simultaneous execution of two or more programs by a single processor executing two or more. So that is multitasking. Okay, so what appears to be simultaneous execution is actually concurrent execution. So that's an important point also, that now if it is appearing to be simultaneous execution, but is actually a concurrent execution. So this is back to the earlier days of Windows. So this is the basic idea of multitasking, that suppose a single processor is performing or executing two or more programs. Okay, if a single processor is executing two or more programs, it has been known as multitasking. Let's go to the next slide. Okay, so think of multitasking this way, that a processor is going to run a program 1 or program 2. So it is just acting as a switch. Now if we switch on one program, the another program will stay in idle state. Another program 1 will be executed, another, and after executing of the program 1, the switch will move on to the program 2, and the program 1 will go into the idle state and the program 2 will be executed. So basically, that's why it is basically we used to think that processor process program simultaneously, but basically it's a concurrent. In case of multitasking, it's a concurrent process, that one at a time it will execute one program. Okay, so but that's why it's known as multitasking. It means basically we have more than one task in our hand and we are performing the task simultaneously. It means we handle one program and we handle second program immediately. So at a time we are curating one program at a time, but basically the whole thing is happening so fast that we are not being able to understand or cope with the basic deep hardware architecture or the software architecture that are being propelled or used to create that kind of an environment. So this is the multitasking. This is the basic definition of multitasking, how it works. So let's go to the next slide. So there are, now we are going to understand two types of multitasking. One is cooperative and another one is preemptive. So first we are going to understand both of them. Okay. So first one is cooperative. So let's understand what is cooperative means. So cooperative multitasking is the same thing here. The applications control the switch. So this is the basic definition of cooperative multitasking. It means the same here. We already know what is multitasking means. There is a concurrent operation of processor on program 1 and program 2. Program, if at a time the program 1 or program 2 will be activated, another one will be an idle state and vice versa. But now the switch, the control of the switch, if the application is controlling the switch, it is known as cooperative. Okay. So if the whole application is in the control of the control switch, it will control how much time the program 1 will be run and how much time the program 2 will be in idle state, or in case of program 1 or program 2. So this is the criteria. The application will control the switching process. So in case of that, it is known as cooperative multitasking. Okay. So let's go to the next slide. And another one is the preemptive multitasking. And how it works, that the operating system controls the switching. So understand, the first one is the application. The application controls the switching. So we have already understood what is multitasking is. So basically there are two differences. One is cooperative and is preemptive. In case of preemptive, the applications will control the control switch. Okay. The application controls the switch. The application means the application suite software. So in case of cooperative, the application or the instruction set will control the control switch. But in case of preemptive multitasking, the operating system controls the switch. It means we can't change it. Okay. This is the basic definition of what it means by that. In case of a preemptive, the operating system has the whole control for the all time of the control switch. So using any kind of software, if we can write thousand pages of code, but it will not going to happen. It means it is already being done. It is already been decided. Okay. So that's why it has been known as preemptive. And the other one, the cooperative multitasking, it is basically known as non-preemptive. So these are the two things that we need to discuss. That in case of non-preemptive, the application or the software part will control the control switch, but in case of preemptive part, the hardware or the OS basically, which are already been embedded within the system, will control the control switch of the processor. Okay. Control the switch basically. Okay. Okay, let's go to the next slide. So this is the proper picture of a multitasking situation here, that there are processor that has been used. This is the program 1 that has been fed, and this is the program 2 that has also been fed, and the output, in case of output, this is a concurrent situation and it has been happening very fast. Each case only one program has been executed or has been executed. So, and according to that, the processor output will come. So this is the multitasking, which has two different categories. One is cooperative or non-preemptive, another one is preemptive. In case of preemptive, the whole multitasking operation has been controlled. Basically, the switching process will be controlled by the operating system. But in case of non-preemptive, the application should practically control the control system. Okay. So let's go to the next one. Now, on this slide, we are going to understand what is the multi-threading means. And so first we will understand what is threading means. Then we will understand what is multi-threading. So first one is a single program or application can be written so that it can be executed as two or more threads of instruction. A thread can be thought of a standalone task. So first of all, we have to understand what is thread. Here the definition is saying. So in this segment, we will understand what is thread. So the definition is saying that a single program or application can be written so that it can be executed as two or more threads of instruction. It can be written so that it can be executed as two or more threads of instruction. So what is thread means? A thread can be thought of as a standalone task. So this is the reason that it got bit confused when you get into the deep of multi-threading, multitasking, multiprocessing. So multitasking, in case of multitasking, what will happen that there will be a concurrent option. The program will be executed using the processor. Processor can execute the application or program. Now, in case of multi-threading, what will happen that a single program, a single program or application can be written so that it can be executed as two or more threads. That's a very important point. The task, in case of task, it is different programs. But in case of threading, a one specific application can be split into three or more threads. So a thread can be thought of as a standalone task. Okay. For example, in a video processing application, the video information could be processed as one thread, the audio as another. Because basically what you are creating, you are creating a video. Okay. So video processor, what will do? It will process the video individually and the audio also are in a different space. So what will happen? Both the video and the audio are a standalone task and both are thread. And how it will be a thread? Because a part of a single program. Now that single program has been split into two, one video processing and one audio processing, but both are basically threads. Now that's why it is called as multi-thread, because there are a number of threads. Now this thread is basically work as a standalone task, but basically it could be named as a standalone task, but basically it is a part of a specific program. So this is the multi-thread. Now multi means more than one thread. So this is a thread that can be thought of as a standalone task. So today we are going to end this lecture with the understanding of multi-threading. Now in the next we are going to explain the multi-threading, how the multi-threading works, how the multi-processing works, what is the difference between multi-threading, multitasking and multi-processing. After that we are going to continue this lecture in the next topic in the next lecture also. So let's go to the so we are going to conclude here today. Okay, so in the next lecture we are going to understand all the multiprocessing also in a deep